Today, we will explore the world of logic and computers. We'll start with the computer itself and dive into the world of transistors, the fundamental components of all modern electronic devices. A transistor is a type of semiconductor device that can conduct and insulate electric current or voltage. In simple terms, a transistor acts as a switch and an amplifier. In other words, a transistor is a miniature device used to control or regulate the flow of electronic signals. Transistors are one of the key components in most electronic devices today. They were developed in 1947 by three American physicists, John Bardeen, Walter Brattain, and William Shockley. The transistor is considered one of the most important inventions in the history of science. A typical transistor is made up of three layers of semiconductor material, or more specifically, three terminals that connect it to an external circuit and carry electric current. A voltage or current applied to one pair of terminals controls the current through the other pair. Here are the three terminals of a transistor. 1. Base. This activates the transistor. 2. Collector. The positive terminal of the transistor. 3. Emitter. The negative terminal of the transistor. The basic working principle of a transistor is that no current flows between the collector and emitter unless a bias voltage is applied to the base. When sufficient voltage is applied to the base, the transistor enters a conduction state, allowing current to flow between the collector and emitter. A transistor functions as a switch or gate for electronic signals, opening and closing electronic gates many times per second. Transistors enable electronic circuits to operate at very high speeds, even up to hundreds of gigahertz, which means more than 100 billion on and off cycles per second. First, let's explore the NOT gate, one of the simplest yet essential logic gates. This gate works by inverting the input value. If the input is 1, the output will be 0. Conversely, if the input is 0, the output will be 1. Due to its ability to reverse signals, the NOT gate is often called an inverter and is widely used in digital logic to produce the opposite of a given condition. Next is the AND gate, a logic gate used to ensure that all conditions are met. This gate has two inputs and produces an output of 1 only when both inputs are 1. If either or both inputs are 0, the output will be 0. The AND gate is critical in systems that require all conditions to be true before taking action. Now we'll look at the OR gate, which is used to determine if at least one condition is met. Like the AND gate, it also has two inputs. If either or both inputs are 1, the output will also be 1. However, if both inputs are 0, the output will be 0. The OR gate is useful in scenarios where satisfying even one condition is enough to take action. In modern digital systems, logic gates are often combined to create more complex circuits. A combination of NOT, AND, and OR gates enables computers to perform various logical operations easily. Let's explore how these gates can work together in a circuit to process inputs A and B to produce a more intricate output. 1. NOT A. This inverts the value of input A. If A equals 1, then NOT A equals 0. If A equals 0, then NOT A equals 1. 2-point AND gate. A and B produces 1 only when both A and B are 1. 3-point OR gate. A OR B produces 1 if either A, B, or both are 1.1. Here's a brief clip of the process of creating this video.